Fluids are in and around us. Roughly 60% of a healthy adult body is made of water. We intake fluids and we move in them. They surround us every moment of our lives from birth to the present. And for this reason, biofluid mechanics is a fundamental area to understand for anyone working in the healthcare arena. Whether you're someone in direct patient care, a pharmacist dispensing medications, or a bioengineer designing the next device. This is an introductory lecture in a series of lectures on biofluid mechanics. We will break this down into 4 parts: bio, fluids, and mechanics, and bring them all together at the end to explain the applications of biofluid mechanics. First, let's look at mechanics. Mechanics is a branch of science concerned with laws of motion. This is divided into 3 main subcategories: statics, kinematics, and dynamics. Statics deals with the equilibrium of forces in absence of motion. In other words, something at rest. Now you might be thinking, in the human body, fluids for the most part are in active motion, and you'd be correct. But we still use certain static principles in medicine, since static principles represent the basic stress state in every fluid, and motions may induce modifications on top of this fundamental state. One of the most commonly discussed principles is hydrostatic pressure. Hydrostatic pressure is simply a type of water pressure that water exerts on a surface when it's standing still. However, we also see this while a fluid is in motion. One example of this is within the capillaries. Hydrostatic pressure allows for fluids to be pushed into the interstitial space. This is one way we apply static principles in understanding biofluids. Kinematics deals with studying motion without the actual forces which cause the motion. Kinematics tries to answer how something moves. Measurements used in kinematics include distance, velocity, and acceleration. This is often used in movement analysis studies, for example, gait studies in Parkinson's disease and post-stroke. As you see here in a gait study, they would measure the leg extension angle, and this would be a kinematic parameter as it describes the angular displacement of a walking movement. And yet, we are not asking anything about the forces that cause this motion, but purely measuring the displacement, and that is what kinematics is. While kinematics asks the how, dynamics is asking why a motion happens the way it happens. It is the study of various forces and causes that create the motion. It deals with investigating and understanding blood flow in our cardiovascular system, or airflow in our pulmonary system. By understanding the various forces involved in the dynamic flows, we can make simulations that allow us to create diagnosis and treatment modalities. Fluids, by definition, are any material that flows and takes shape of their container. Fluids include liquids and gases, and less talked about state of matter, plasma. We make clear distinction between solids and fluids. Solids, for the most part, have a relatively rigid and fixed shape, while fluids flow and adapt to the shape of their container. This is primarily due to the arrangement of atoms on a molecular scale. With solids, the molecules are tightly packed in a fixed arrangement. This is due to the strong intermolecular forces, and these forces allow solids to maintain both shape and volume. Liquids, on the other hand, are still close together, but not in a fixed arrangement. This is due to the weaker intermolecular forces than solids, which allows for liquids to take the shape of their container while still maintaining a constant volume. In gases, molecules are far apart and move freely. The intermolecular forces are very weak, and they spread out and fill the entire volume of their container. So not only do they not have a rigid shape, but they don't maintain the same volume. For plasma, the molecules are ionized and have even more energy than in gases. the intermolecular forces are negligible, and charged particles move freely. Plasma needs special methods to be contained, unlike gases, otherwise it can become unstable and disperse. Another way to look at solids and fluids is in their ability to flow and deform. If we have two plates, and the one plate on the bottom is stationary, while the one on top is moving with a force F, this will cause a shearing stress at point of contact with either the solid or the fluid. Shear stress is simply a stress felt parallel to a surface. The solids resist an applied shear stress by deforming until their elastic range limit is reached and then stop deforming. But fluids deform continuously under the influence of shear stress, no matter how small. It must be highlighted that the exception to this are viscoelastic materials. These include our tendons and ligaments. These are solids with fluid-like properties. They deform and flow over time under shearing stress, although initially having more elastic deformation like solids. Now let's look at bio. Bio is simply shortened for biological. So biofluids is referring to biological derived fluids. In terms of what biofluids entail, it is a very long list. This can include more well-known ones such as blood, mucus, urine, synovial fluid. What's often not discussed is foreign fluids that interact with a living organism in a biological aspect, as these are also considered biofluids. These would include the air that we inhale, intravenous fluids such as normal saline or D5W that are injected, vaccines that are administered. Imagine every foreign fluid that comes into contact and interacts with body's biological systems. These would be considered biofluids. Bringing it all together, in summary, biofluid mechanics is studying how fluids such as blood and inhaled air interact with biological systems like our cardiovascular system and pulmonary system. Some examples of applications of biofluid mechanics include designing heart valves, stents, and drug delivery methods such as colloidal particle systems and nano carriers. The applications of this field are vast and growing. We'll be exploring more into the different applications in future videos in the series. Please subscribe to the channel and like our video if you found this video useful. We have more information in the description under the video on additional resources on this topic and ways you can help support this channel. Thank you.